Today we're going to be doing a second order non-homogeneous differential equations problem that is also an initial value problem. So in this particular case we've been given the function y double prime, or the second derivative of y, plus 3y prime, or the first derivative of y, minus 4y is equal to 2e to the x, and we've been given two initial conditions, y of 0 equals 1 and y prime of 0 equals 2. I've also got a formula here for y of x, and we'll talk about that in a little bit. So the thing that makes this second order is the fact that we have the second derivative here of y. That's what makes it a second order differential equation. It is non-homogeneous because it's equal to 2e to the x. Whenever your second order differential equation is equal to anything other than 0, it's non-homogeneous. And it's an initial value problem because, of course, we have initial conditions here that we're going to be plugging in. So I've written down the steps that we're going to use to solve this. The first thing we're going to do, and we'll do these steps as we work through 1 through 3 here. The first thing we're going to do is find the roots of the differential equation and use them to write the general solution. So remember that when you're finding roots of a second order differential equation, you can, even when it's non-homogeneous, ignore the right side. So even though we have 2e to the x over here on the right, we can ignore that for now, and we're going to just treat that as 0 in order to find the roots. We will also, while we're at it, go ahead and change these y double prime, y prime, and y terms here, or variables, into r. So the trick I always use, and you'll see this in my other videos, is I count the number of, just so I remember, the number of hash marks here on the y. So because there's 2, I'm going to change this into r squared. 2 hash marks, this is going to be r squared. Plus 3, we have 1 here on this y, so that's going to be r to the 1, r to the first power, which of course will just be r. And then here, because we have 0 hash marks, we're going to have r to the 0 power. Of course, anything raised to the 0 is just 1, so this will be negative 4 times 1, or in other words, just negative 4. So that's how I remember how to change the original function into something with an r variable that I can deal with. So this is the function we're going to use to get our roots. What we need to do is factor it. So I can easily factor this one, luckily, so I'll get r plus 4 times r minus 1 equals 0 will give me positive 3r in the middle and a negative 4 here. So I can factor it, and I can see after I factor that I'm going to get r equal to either negative 4 or positive 1. If I solve this first equation here, r plus 4 equals 0, I'll get r equals negative 4. When I solve r minus 1 equals 0, I find that r equals 1. So what this tells me here is that I have two roots. They're both real numbers, and because they're different from one another, they are distinct, or we like to call it distinct real roots. If I had gotten, for example, negative 4 and negative 4 as roots, that would be equal real roots, and the equation I would use here, y of x, would be different. This equation, y of x, is specifically for distinct real roots. Go ahead and review the second order differential equations chapter of your book, or on my website I've got some different examples of equal real roots, distinct real roots, complex conjugate roots, etc. So depending on what kind of roots you have is going to determine the formula that you're going to use. When you've got real numbers and they're different from one another, this will be the one you'll use. So we'll go ahead and write y of x, and we're still on the first step here. Y of x is going to be the general solution, as we've indicated here, general solution. So y of x, we'll go ahead and leave c sub 1 and c sub 2 as constants. What we're going to plug in for are r sub 1 and r sub 2. So we'll go ahead and say that r sub 1 is going to be negative 4. We'll go ahead and just color code this so that we don't get lost here. And positive 1 will be our second real root, so we'll call that r sub 2. So we're going to get c sub 1 e to the negative 4x plus c sub 2 e, and because we have 1 here plugging in for r sub 2, we'd get 1x, which of course is just x. So this is now our general solution, and we're done with step 1. We found the roots, and then we wrote the general solution. So our next step is going to be to identify the particular solution, which we'll call y sub p, as opposed to the general solution, which we're just calling here y of x. When we find the particular solution, we're then going to move on to finding the first and second derivatives of the particular solution, and we'll plug all three of those back into our original function. So when it comes to finding the particular solution, and again, we'll call it y sub p for the particular solution, what we're going to want to do is find a particular solution that models the right-hand side of our function. So we have on the right-hand side 2e to the x. So normally what you're going to want to do is plug in constants like a and b for constants that we have in our right-hand side over here. This can be a little bit tricky and take some practice, but in this case, my first guess would be a e to the x. We would replace 2 with a because we don't know exactly what the constant is going to be in our final solution. So we would replace 2 with a and we would leave e to the x here. What we need to be careful of is this is close to what our actual particular solution is going to be. But no matter what particular solution you end up with, you always need to compare it to your general solution. So what we see here is that we have a e to the x in our particular solution. If you notice, and let's go ahead and box these, we've got a e to the x here in our particular solution. In our general solution, we have this here, c sub 2 e to the x. Well, c sub 2 and a are both constants. So really, the two of these things, a e to the x and c sub 2 e to the x, have exactly the same form. So if we just write a e to the x for our particular solution, it's going to get messed up with this c sub 2 e to the x, and we're going to run into an issue later. If you try using a e to the x for your particular solution, you'll see down the road that you'll have an issue. What we have to do is, at the very least, change the particular solution so that it is in some way distinct from each of the terms in our general solution. So the way that we're going to do that is by adding in an x. So instead of a e to the x, we're actually going to make our particular solution a x e to the x, which makes it fundamentally different from both c sub 1 e to the negative 4x and c sub 2 e to the x. So we'll call ax e to the x our particular solution. Once we've found our particular solution, we need to find the first and second derivatives of our particular solution. What we're going to end up doing is plugging in for y here. We're going to plug in our particular solution here for y. We're going to plug in the first derivative of our particular solution here for y prime. And we're going to plug in the second derivative of our particular solution for y double prime. So let's go ahead and find y prime, or the first derivative of our particular solution. We're going to need to use the product rule. So we have one function here, a of x, and a second function here, e to the x, right? So in order to take the derivative of these two functions that are multiplied together, we need to use the product rule. So remember that the product rule tells us we'll take the derivative of one of the functions, leaving the other one completely alone, and then add to that the opposite combination. So we'll take the derivative first of a to the x. The derivative, ax, a times x. The derivative of ax is simply a. So since we took the derivative of that function in blue, we just go ahead and leave the purple function completely alone. But then we have to add to that the opposite situation, where we leave a sub x alone and we take the derivative of e to the x. Well, when we take the derivative of e to the x, that's simply e to the x, right? Because the derivative is the exact same thing. So what we got here was, this was the derivative, and this was the original a to the x function. This was the original e to the x function, and this was the derivative of the e to the x function. So that is our first derivative. Our second derivative, y double prime, is going to be, well, when we take the derivative of a e to the x, remember that a is just a constant. It's not a variable, so we don't have to use product rule in that case. It's the same thing as saying, for example, 3e to the x. The derivative of that, of course, would just be 3e to the x, exactly the same thing. we wouldn't have to treat 3 as a separate function. So a e to the x is the same case, and the derivative of that is still just a e to the x. Ax e to the x, however, we end up with the exact same situation. Notice here that this is the same as our original function there. So the derivative we already know is going to be this whole thing here. So we'll get a e to the x plus ax e to the x for our second derivative. Notice that we have one a e to the x and a second a e to the x. So this is going to simplify to 2a e to the x plus ax e to the x. So now that we have our first and second derivatives, we'll go ahead and plug those in to our original function. So let's go ahead and we'll note these in specific colors. So we're going to plug this 2a e to the x here in for y double prime. We'll plug this function here, a e to the x plus ax e to the x, the first derivative, in here for the first derivative. And then we'll plug the original function here, y sub p, in for the original function here, y. So those are the three substitutions we're going to make. So we'll get 2a, here pulling from the second derivative just above this, 2a e to the x plus ax e to the x, plus 3 times the first derivative is a e to the x plus ax e to the x, minus 4 times the original function, so a e to the x, oops, sorry, I boxed too much over there. What we should be looking at is just this part here, ax e to the x, because we changed that. So ax e to the x. And when we plug those three things in, we're going to go ahead and set that equal to the right-hand side, 2e to the x. And now we just want to go ahead and solve for a. So in order to solve for a, we'll just go ahead and multiply out these terms here. So we'll say plus 3a e to the x plus 3ax e to the x minus 4ax e to the x equals 2e to the x. So now we'll need to combine like terms. So we have here, and let's do this in a different color, we have 2a e to the x, we have 3a e to the x, and then we have, that's it. So we'll get 5a e to the x. Then in different color here, we have 1ax e to the x plus 3ax e to the x is 4ax e to the x minus 4ax e to the x is going to give us ultimately 0. We've got 1 plus 3 is 4, minus 4 is 0, so that's going to go away completely, and we'll just be left with equals 2 e to the x. Now, when we divide by e to the x, both sides by e to the x, this is going to go away, and we're going to be left with 5a equal to 2. When we divide both sides by 5, we'll find that a is equal to 2/5. So notice here, if we revisit our steps, we identified the particular solution. We found that here as y sub p. Then we found y prime of p and y double prime of p. We got those here and here. Now we plugged those into the original function and we solved for constants. We found that a was equal to 2/5. Now notice that in step 3, we need to add the general and particular solution together to get y of x, and then we're going to find the first derivative of y of x so that we can use our initial conditions, y of 0 up here and y prime of 0, to find c sub 1 and c sub 2. So let's go ahead and give ourselves some room here. We don't need our roots anymore, we just need our general solution that we found. So we found here our general solution y of x, and we also found our particular solution there. What we want to do, since we found that a was equal to 2/5, we know that our particular solution instead of ax e to the x is going to be equal to 2/5 x e to the x. So when we find the constant, we plug it back in here to our particular solution. So now we've got our general solution here up top, and then our particular solution just beneath it. So I want to go ahead and leave those, and we will combine them. So now that I have these two, I'm going to add them together to find y of x. So y of x is going to be my general solution, c sub 1 e to the negative 4x plus c sub 2 e to the x. And I'm going to, in order to get my general solution, add my particular solution to it. So I'm going to say plus 2/5 x e to the x. And now I no longer need these. So now I'm on step 3 and I've got my general solution here, y of x. So I got y of x. Now I'm going to find y prime of x because I'm going to need both of these in order to use my initial conditions. Notice I have an initial condition for y of 0. This initial condition is going to get plugged in here to y of x. And my second initial condition is y prime of 0. That's going to get plugged into our derivative function, our y prime function. So in order to take the first derivative, remember that I'll be treating c sub 1 and c sub 2 as constants. So the derivative of c sub 1 e to the negative 4x will be negative 4 c sub 1 e to the negative 4x. The derivative of c sub 2 e to the x, again, will just be c sub 2 e to the x. And then for my 2/5 x e to the x, I have to treat this as a two-part function here. We're going to need to use product rule again because I have two functions that are multiplied together. So we'll take the derivative of the first, 2/5 x, the derivative of that is just 2/5. So then we'll multiply that by the other function, e to the x. But we have to add to that the opposite situation. So in this case, we'll leave 2/5 x alone, and we'll take the derivative of e to the x, which again is just e to the x. So there's our first derivative. So we found y prime, and now we're on the last part of our step. We're going to use our initial conditions. We're going to plug each of them in to y of x and y prime of x to solve for c sub 1 and c sub 2. When we find c sub 1 and c sub 2, we're going to end up plugging those back into this function to find the general solution. So again, we will plug in here our first initial condition, y of 0 is equal to 1. So over here, let's erase this. Over here, we'll get y of 0, we'll plug in 0 for x, is going to be equal to c sub 1 e to the negative 4 times 0 plus c sub 2 e to the 0 plus 2/5 times 0 e to the 0, and that's all going to be equal to 1. That's what our initial condition tells us. We plug in 0 for x, and whatever we get is going to be equal to 1. So we set that equal to 1. When we solve this, we'll get here e to the 0. Anything raised to the 0 power is 1. So this e to the 0 is just going to become 1, which will just leave us with c sub 1. Same thing here, e to the 0 gives us 1, so we end up with c sub 2. And this whole third term, 2/5 times 0 times e to the 0, will be 0, of course, so we'll just get c sub 1 plus c sub 2 is equal to 1. Now, in order to solve for c sub 1 and c sub 2, we need a second equation. So we're going to use our second initial condition, and once we get an equation with just c sub 1 and c sub 2, we'll solve using simultaneous equations. So here, for our second initial condition, we'll plug in 0 for x and set it equal to 2. So we'll say y prime of 0 is equal to c sub 1 e to the, wrong thing. So remember here, I'm looking at the first equation. Remember that we're plugging in to this equation here. So we'll actually get negative 4 c sub 1 e to the negative 4 times 0 plus c sub 2 e to the 0 plus 2/5 e to the 0 plus 2/5 times 0 e to the 0, and that's all going to be equal to 2. Sorry for getting kind of smushed here. So now we'll have, you can see, e to the 0, so that's going to be, of course, 1. We'll get negative 4 c sub 1. Again, e to the 0 will give us 1, so we'll just be left with c sub 2 here. E to the 0 will be 1, so we'll have 2/5 for our third term, and then our last term will be 0 because, of course, it's multiplied by 0, and that's all set equal to 2. So now let's go ahead and subtract 2/5 from both sides. So we'll get negative 4 c sub 1 plus c sub 2 is equal to, let's change this 2 here into 10/5. So we have a common denominator with this 2/5. So the 2/5 will cancel over here. We'll subtract 2/5 from this side, and you can see that over here on the right, we'll get 8/5. Okay, so now we have two equations here. We've got this one, c sub 1 plus c sub 2 is equal to 1, and this one, negative 4 c sub 1 plus c sub 2 is equal to 8/5. We need to solve those using a system of simultaneous equations. So let's go ahead and do that over here. We'll say c sub 1 plus c sub 2 is equal to 1. And then we have over here negative 4 c sub 1 plus c sub 2 is equal to 8/5. So we want to cancel one of these variables so we can solve for the other. If we subtract here, if we subtract this entire second equation from the top equation, the first equation, notice that the c sub 2's will cancel because we'll have a positive c sub 2 in the top minus a positive c sub 2 is going to give us a 0. So let's do that. We have, for the negative 4 c sub 1, a double negative. We've got minus negative 4 c sub 1, so that's going to turn into a positive, and we'll end up with 5 c sub 1. The c sub 2's will cancel, and then over on the right-hand side, we'll have 1 minus 8/5, which will give us a negative 3/5. So now, if we divide both sides by 5, we find that c sub 1 is equal to negative 3 over 25. So that's our first constant. We can now plug that back in to this top equation, which looks pretty simple here. We'll get negative 3 over 25. We plug that in for c sub 1, plus c sub 2 is equal to 1. When we add 3 over 25 to both sides, we'll find that c sub 2 is equal to 28 over 25. And now we have our two constants. So our last step, let's go ahead and erase everything over here on the right-hand side so that we can write out our final answer. Our last step, now that we have c sub 1 and c sub 2, we use the initial conditions to solve for constants. We're going to now plug those back in to our original equation. So we've got c sub 2 here, and we have c sub 1 here. So we want to plug these in to get the solution. The solution will be y of x equals, we know that c sub 1 is equal to negative 3 over 25, so negative 3 over 25 e to the negative 4x, and then we have c sub 2 as 28 over 25, so plus 28 over 25 e to the x, and then, of course, from our particular solution here, plus 2/5 x e to the x. The only thing I would consider doing here to simplify, whenever possible, we don't want to lead with a negative, so we'll switch this around to be 28 over 25 e to the x minus 3 over 25 e to the negative 4x plus 2/5 x e to the x. And that, y of x here, that will be our final answer for this second order differential equation initial value problem. So that's it. I hope this video helped you guys, and I will see you in the next one.